Let's continue with the second talk of this morning session. So I would like to introduce Azalea Raad. Azalea is a senior lecturer at Imperial College in London, and she's very well known for her work in program verification and program logics. In particular, she's done a lot of work on concurrency and especially weak memory concurrency. And more recently, she has looked more into bug finding tools based on incompleteness logic and techniques like that. So before becoming a senior lecturer there, she did a postdoc at Max Planck in Saarbrücken in Derek Dryer's group, and she got her PhD also from Imperial College, working with Philippa Gardner and Sofia Drosopoulou. And she has the coolest URL of all my colleagues. Her website is soundandcomplete.org, which I think is amazing. So great to have you. Please go ahead.
Thank you so much, Peter, for that lovely introduction. And thank you all for having me here, especially before lunch. I always hate having this spot because I'm the only thing standing between you and lunch. So hopefully, please bear with me. I'm going to tell you a little bit about a few pieces of work that we've been doing on incorrectness logic and how we've been using it for scalable bug detection. So before I can actually tell you about incorrectness logic, I need to give you a tiny refresher, especially because this is before lunch, on how we've been doing verification so far in the last 2 decades and why we wanted to change that a little bit. So over the last 2 decades, there has been lots of program logics, different styles of reasoning about programs and verifying them, and a lot of tools, static analysis tools specifically, based on those approaches. So these approaches are like what we call them correctness reasoning, specifically meaning that we use them to prove the absence of bugs in programs. We want to verify them to show that they don't have any bad behaviors. And these are instances of reasoning that what we call over-approximate reasoning, meaning that we overestimate the set of possible program behaviors, because if we can manage to show that this over-approximate set of behaviors doesn't have any bugs, then by definition, the actual set of program behaviors, which is smaller, is not going to have any bugs either. And again, in the last 2 decades, unless you've been under a rock, because of things like separation logic, there have been a lot of advances in compositional reasoning, where we can reason about code fragments rather than global, whole programs. So we can reason about incomplete programs, different bits of programs together, and glue them together to get the whole result of the program analysis. And this is also something that allows us spatial locality. You'll see an example of what I mean by that in a second, meaning that we can only talk about the actual resources, like let's say bits of memory that the program accesses, and then things like separation logic, again, give us that spatial compositionality, meaning that we can then extend that specification that we have to bigger context, which is really important for scalability. So, like I said, there have been lots of formalisms for correctness reasoning, but the essence of all of them can be captured in the style of Hoare triples. Even separation logic triples are an instance of a Hoare triple with a different model. So what is a Hoare triple? Again, I'm probably preaching to the choir here. This is ETH, so a lot of you already know this. But essentially, this triple says that given any state, initial pre-state S in P, if I run C on top of S and the program terminates, then I'll end up in a post-state S prime that satisfies Q. So in other words, Q is a superset of all possible post-states, all possible program behaviors, essentially starting from P. And this is exactly what I mean by this is an over-approximate kind of reasoning, because we are considering a potentially bigger possible set of program behaviors. And like I said, this is good because we want to show that there are no bugs. So if you do it for a bigger set, then the actual program is not going to have any bugs either. Pictorially, we are in this situation. This black inner oval, which one is the... do we have a... Oh, yeah. It's just not... Okay, bad fail. So if this... So you can think of this set of post-states, the actual program behaviors, as this smaller inner oval, and Q being this over-approximated set of possible behaviors, which is to say, yes, if Q doesn't have any bugs, then there is no bug in the program either. But as a lot of you in this room know, verification in general is a very hard problem. Proving that the program is correct is a very hard problem. Not in the least because you have to consider every possible program behavior, and also for practical reasons like reasoning about loops, coming up with loop invariants and things like that. So over time, we gave up over our noble dream of verification, and we said, okay, what if we instead focused on bug catching? We can't prove the program's correct, also because often the programs aren't correct. So what would help the developer is that if we manage to actually find bugs and tell them, hey, here's a bug, go fix it. So we flipped things around and said, okay, we'll use these formalisms for bug catching. And here is when we got into a little bit of a pickle. Because what would often happen, which is great, is that you would identify bugs that are actually in the set of possible behaviors, in the set of post states, and that's great. That's what we call a true positive. But because Q is an overestimated, over-approximate set of possible program behaviors, there would typically be cases where you would find a bug, report it to the developer, and it would turn out that this is not actually a real bug, because it's in Q in this overestimated set, but it's never really reachable. So we would report this to the developer, they would get really annoyed, saying, no, this is a false positive, this never arises, why are you spamming me with all of this? So we kind of had a clash of principles here because we were using a formalism designed for verification, for showing the absence of bugs, but we were deploying it to show the presence of bugs. So, the principle and the practice were clashing together. And this is exactly the story of Peter O'Hearn, for those of you who know him. So he's obviously the figurehead behind separation logic, and then they had the Infer tool, which was bought by Facebook, and he spent years at Facebook trying to use Infer for bug detection. And over time, the developers started losing faith in Infer because of the high number of false positives. So at this point, Peter was like, okay, you know what? The number one axiom, the mantra of verification should be not to spam developers. So don't report anything to them unless you're absolutely sure that, or at least have a high degree of confidence that it's a true positive. Notice in this clash in principle and the clash between principle and practice is that, okay, maybe we need to start from the beginning and change the way we think about bug detection. And this is where he introduced incorrectness logic, which is a formal foundation not for verification, but for bug catching. So this was all a very long prelude into what is incorrectness logic. So let me actually tell you what incorrectness logic is, which is this first part of my talk. Right, so remember the whole triples? You saw it, the over-approximate set. So very straightforwardly, the problem I said here is that Q is bigger than the set of possible behaviors, right? So let's take that and flip the subset inclusion, and this time we will under-approximate the set of possible program behaviors. And since I flipped the direction of subset inclusion, let me also just write it in a different style with these square brackets. Now this time, this incorrectness triple says that every state in Q, every post state in Q, is reachable by running C over some pre-state S prime. So you can see that Q is under-approximating the set of possible program behaviors because of this flipped direction of subset inclusion. And pictorially, we are in this situation. I'm sorry for those of you who are in the back, you have to kind of wiggle a little to see it. But the point is now Q is actually smaller than the set of program behaviors. So any bug I report, by definition, is going to be a true positive. It's going to be a reachable bug, an actual true positive. And the flip side is that we can potentially miss some bugs because we are considering an underestimated set of program behaviors, but this is okay because our mantra, remember, our number one priority was to eliminate noise, eliminate false positives, even if it is at the price of missing some potential bugs. Okay, so I now want to tell you a little bit more about incorrectness logic and then our extension with separation logic, but I want to show you two tiny bits of technical details. First, that the incorrectness triples have one extra component, this epsilon, which is the exit condition, that talks about how the post state came about. Was it as a result of a normal execution? Did the program terminate normally? Or was it an erroneous execution? And this is useful, you'll see, for identifying bugs. Something happened. Okay. So for instance, if I assign y to x, if I write the value of y to x and y initially holds value v, then obviously the program will terminate normally, no problems, and afterwards they both will hold value v. By contrast, if I execute an explicit error instruction, you can think of it as an assert false, for instance, then the state will be unchanged, but I will terminate erroneously. And these tags are very useful for identifying bugs, as you will see, because you can actually have custom bugs for null pointer dereferences, etc. The second thing I want to show you is an alternative but equivalent representation of these incorrectness triples in terms of reachability. So rather than this subset inclusion that you saw up there, we want to say, so you can think of it as what I said in English before, but written fancily in maths here, that every post state in Q is reachable from some pre-state S prime in P if you execute C over it. Okay, so this was back in 2020. Peter Ahern, that is, because we have another Peter in the room, presented this work at Pavillon 20 and as a first formal foundation for bug catching, and you can think of it as an under-approximate analog of Hall logic. But this is ETH, right? So you guys, at least Peter's group, love separation logic. So this is obviously when people like me, who also have worked in separation logic, realized, Peter, why don't you take it all the way? You know, Hall logic is great, but it only allows you to do global reasoning as a whole program. You can't have this compositional reasoning style that we really like in this community. And also you can't reason about things like memory safety bugs. So that's when I kind of joined Peter Ahern. I started doing some consultancy at Facebook at that time, so we started developing incorrectness separation logic together. And at the risk of boring you, but just because I know there are a couple of people in the room who are not exactly familiar with separation logic, let me give you a quick recap of what that is. Also, again, because you're all dreaming of lunch, so that's an ideal time for you to have a quick nap. So separation logic, like I said, local reasoning via two main principles, ownership and separation. And it's really good for reasoning about heap manipulating programs, especially when you have aliasing. To see a very simple example, imagine I have this program. I'm writing 3 distinct values to locations x, y, and z, and I want to prove that afterwards x, y, and z are indeed hold those values. Right. But I can only do this if I know that x, y, and z are distinct memory locations, i.e. I have no aliasing. Because otherwise, if x and y are aliases, I cannot show that they're both 2 afterwards, not that x is 1 and y is 2, right? But you can see so here is just like a tiny program, but in the context of a large program, when I have essentially 9, like say n of these assignments, I'll need n factorial over 2 conjuncts saying each of these locations are pairwise disjoint. And this can quickly become intractable. So separation logic solution to this is introducing these principles of ownership and separation, and via its assertion language, which I will show you in a minute. So for instance, here we have this x points to assertion that says x is a heap location. It points to some arbitrary value. Here I don't care about it. And it also gives me ownership of that location. So I'll come back to what that ownership means. But the other thing is that I have this other conjunction, the star, which you should read as and separately. So rather than having to explicitly say that these locations are distinct, I can just put a star between them that says these locations are all separate from each other, and I'm done. So I said ownership. What does that mean? It means that this assertion is a linear resource. It can't be duplicated. So you can't have x points to be combined, star separated with itself. You can only have one copy of it at a time. For those of you who are familiar with linear logic, this is essentially an instance of linear logic. Cool. The other key ingredient of separation logic is this framing principle, which actually comes from the world of AI, for those of you who know your history. And this is really cool because it says that if you manage to prove some specification for program C, PCQ, then you can actually run it in other contexts when you have additional resources, let's say a larger heap that also has this R component, by adding it on both sides, provided that the resources that you're tacking on both sides are separate. And it's useful because we can prove the smallest possible specification that we can foresee in terms of the resources that it needs, and then keep reusing it in different contexts. We don't have to write a separate specification all the time. So every time we have a different amount of heap needed, we can tack on those extra bits of the heap. So what we can do, like I said, is write very small axioms in terms of the resources needed, what we call local axioms. So for instance, when I'm trying to write to heap location X, and I have ownership of location X, denoted by this X point to here, I think this is going to be useful. I've also discovered that this is very useful for waking up my students just before lunch. So, because, you can do this. It's a bit louder at Imperial for some reason. I think this is bamboo, so it's quite soft. Anyway, so if I'm writing to heap location X and I have ownership of X beforehand, then afterwards X will hold value V. Unsurprising. Similarly, if I want to read from heap location X and initially it holds value V, I will still have X points to V afterwards and Y is V. Not surprising. If I want to, I should have known that. I couldn't have known that these desks are going to be in the way, so sorry. So if I want to allocate some new heap location, initially I don't need any resources. This is denoted by this emp session that says I don't need anything. So I just can start this on an empty heap. And afterwards, I'll return an arbitrary value, this existentially quantified location, which will hold another arbitrary value, and I will return that location in X. And the cool thing about emp is that you can think of it as the identity of star. So, it's like true in classical logic. So anything star emp is it's idempotent. It's equivalent to P, because emp gives you empty heap. And dually, if I want to deallocate X, provided that I have the ownership of X to begin with, then I can free it, get rid of it, and end up with emp again. Okay, so that was you can wake up now. That was my brief introduction to separation logic. So I've shown you incorrectness logic. You now know what separation logic is. Now I wanted to combine this and get the separation and ownership and stuff in the incorrectness logic world. So in a nutshell, this is the picture we wanted. We wanted to have this framing principle in incorrectness logic with the same kind of composition axioms. So being lazy, of course, our first attempt was just to simply translate those axioms, those properties that we had for heap operations, into the under-approximate world. And for a while, it looked like things are going to work. So let me quickly go through this. So this is exactly the axiom that you saw for separation logic. It says that if you write to X and you have ownership beforehand, then the value changes in the post state. And this will be a normal execution. But another cool thing that we can do is actually talk about erroneous execution, something we couldn't exactly specify in separation logic, saying that if you try to write to heap location X, but X is null, then obviously you'll get an error because this is really a null pointer dereference. You can't write to a heap location that is null. Analogously for Raad, this is exactly the axiom that you saw in the correctness analog separation logic, but we also have the null pointer dereference case. Allocation is identical. Yes?
So what is the predicate just after that error annotation? Is that the reason for the error, or is that
it says that all these state is reachable. This is the post state. It's exactly like in whole logic, except that the interpretation is flipped. So this is describing any state in which X is null. So it's saying you can, if X is null, you will get a null pointer with the reference from X points null. And in general, for erroneous triples, the state doesn't change, because if you have an error, they are usually side effect free, and they just hit an error. So you just carry it forward.
Sorry, follow-up question. Are you using that to catch the exception, for instance? Can I catch an outpoint the exception and then know that this prediction is true?
Yeah. So allocation is unchanged, and we did the same thing for free and said, okay, I'll just recast that exact same triple with a no case back and the null pointer dereference. And unfortunately, this is when things broke, especially the introduction of this free axiom broke the beloved frame rule of separation logic, which is what we wanted for compositionality. So let me show you why things break when you add this free axiom. So remember, this is my absolute must-have. I want to preserve this property for compositional reasoning, and this is the axiom that I just wrote in the under-approximate world. So what I can do now is use this frame rule and tack on extra resources on both sides. Specifically, I can add on X points to V on both sides of my triple. And now if you look at these rewrite rules that I have here, I can rewrite the left-hand side as false, because this is a linear resource. It can't be confined with itself, and M is identity, so I get X points to V. And this is where things break, because if you look at the interpretation, that reachability thing that I said, this is now saying the heap in which X points to V is reachable by allocating X, deallocating X when the initial state satisfies false. So there is some state that satisfies false. You can start from there and reach this state. But there is no state that satisfies false. So you essentially are basically breaking this existential quantification in the interpretation. Because this is saying that this is reachable from some state in false, and there is no state in false. And it turns out the reason for this is because the original separation logic had this non-monotonic model, meaning that the amount of resources that you need can grow or shrink. So it can grow via allocation and shrink via deallocation. And as a result, this free, exactly what I wrote here, this free axiom is lossy. So forgets about the fact that at some point X was allocated and it is now deallocated. We've essentially given up that information. So our solution to that was, very obviously, in hindsight at least, to track the allocated location. So every time we deallocate something, we remember the fact that it's been deallocated. Specifically, if I go back to my free axiom, this was what I had before. If X points to V, it's now emp. I'm going to replace this with this other assertion that says X is deallocated, i.e. at some point before it was allocated, and now it is deallocated. And yeah. So I had these axioms from before for points 2, and I treat this X is deallocated exactly the same way, meaning that this is also a linear resource that can't be duplicated, so it can't combine with itself. It's an ownership, and it obviously also can't combine with X points to, because I can't say X is deallocated, but also X is allocated and holds V. That's just not true, right? So I have these extra 2 axioms for composition. So now if I revisit the example that I just showed you, and repeat the same thing, you'll see that the frame rule doesn't break. Specifically, I'll add this X points to on both sides using my rewrite rules. X is deallocated at X points to V gives me false, and I still have false on this side as well. And now this triple is vacuously true, because it says every state in the post which is false is reachable from some state in false. Ilya? No, and you'll see in a minute. So, going back to my axioms, I have obviously changed free to now say X is deallocated. This is my null pointer dereference from before, and I now actually can add another axiom that says if you try to free X and X has already been deallocated, then you get an error, because this is an instance of a use after free. You're trying to access X to free it after it has already been free. So I can, with this formalism, I can also catch use after free errors. I'll do the same thing for the write and the read. This is exactly what I had before, and I'll add the X is deallocated. And to answer Ilya's question, I basically have the old axiom where I existentially quantify L, so it could be an arbitrary value, but I can also add this specific case because I'm in the under-approximate world that says, you know what, if the location Y is already deallocated, it's possible, because remember under-approximation, not every execution, but there could be executions in which actually your allocator picks that exact location that was deallocated from before and return that. So this is, again, because of under-approximation, this is something we could say here and not in the original separation logic. Okay, so that was the first part of the talk in a nutshell, which was the theory of incorrectness separation logic, where we combined incorrectness logic and separation logic together. It's under-approximate analog of SL for memory safety bugs. You saw that the combination wasn't straightforward. We had to change the model. And one additional benefit that I'm not going to talk about for the theoreticians in the room was that this new model allowed us to recover the footprint property. The footprint property was something that was broken in the original SL, which was the reason separation logic is incomplete. So if you want to have completeness, you need this footprint property. And this monotonic model allows us to recover that. So it was a nice bonus in that sense. And finally, I started the talk by saying things like we need compositional reasoning, we want to have static analysis for bug detection that has, is under-approximate. That was the whole story, right? But then I delved into theory. So really, we wanted to test the metal of our new theory and see if it's actually suitable for bug detection or not. Which brings me to the second part of the talk, our static analysis tool based on under-approximation, PulseX. Yes, Zach.
Maybe a really simple question, but where does the under-approximation come in? All the rules look quite tight.
The under-approximation comes from the...
Rule, like, where does it sneak in, I guess is the, yeah.
Oh, okay. So two things. It comes from the interpretation of the triple that says that the post condition is reachable. But one thing I didn't show you, which is different from Hoare logic, is rules like... if statements. For instance, in the original Hoare logic, if you want to show PCQ holds and C is if then else, you have to show it for both branches, right? For the then branch and the else branch. In the under-approximate world, you only need to show it for one branch. So you just say if one of the branches, and same thing for loops, you have to show it for any number of iterations. Okay, so let me tell you about Pulse X. This is the elevator pitch, getting all the brownie points of all the things that Pulse X has. It's automated static program analysis for memory safety errors, things that you saw, null pointer exceptions, use after freeze, as well as memory leaks. So I didn't show you the formalism for memory leaks, but Pulse X can also detect those. It's underpinned by ISL, which means by construction it doesn't have no false positives, but you see there is a tiny asterisk. So I'm not showing you the full terms and conditions, but I will come back to that in just a minute. It's interprocedural, compositional, biabductive. These are all buzzwords that I'm throwing out there to impress you, but I'll talk about all of this in just a minute. Compositional, meaning that I can begin anywhere and with my analysis with different procedures, which is very important for continuous integration. So you have large teams, for instance, at Facebook, who submit thousands of lines of code of diffs every day, and you want to make sure continuously that the diffs submitted actually don't have any bugs, so we can do that on the diff. We did deploy this at Meta while I was a consultant there, and here are some pithy results. In terms of performance, it was comparable to the over-approximate infer tool, and we were very happy with this because, for those of you who know, at Facebook there is a team dedicated to maintaining infer, and it's got at least 10+ engineers full-time working on making infer better and better, whereas this was a very meager academic tool developed by one engineer, which is my collaborator, Locke. And still, we managed to, over 3 months, build something that was comparable to infer. So we were quite pleased with that. And in terms of its fix rate, i.e. the percentage of bugs that we reported and were actually fixed, it was comparable to infer, but there were actually scenarios like in OpenSSL where we had a higher fix rate because we didn't find false positives. So the bugs that we found were all true positives and were fixed. So that's the summary. So let me tell you a little bit about the actual analysis itself. So in a nutshell, you can think of the analysis result, like what Pulse X does, as first chopping up the program into tinier parts, tinier components, reason about them in isolation, and then combine the result of these individual analyses together to get the overall analysis. That's what we mean by compositionality, right? So what are the parts? The parts are really procedures. So the granularity is every procedure, every function. So we reason about each procedure in isolation. Like, for instance, if F1 calls F2 and so on, then we analyze each one of these separately. And the means of combining them together is really under-approximate by abduction. So this is nothing terribly exciting. By abduction has been around for a long time. It's actually implemented in infer, except that we did the under-approximate version of that, and that had some advantages. Going back to Zach's question, I'll tell you in just a minute. And the analysis result, what we obtained end-to-end, was an incorrectness triple on an under-approximate specification of the whole program. So a little bit more about that. So I said we analyze each procedure in isolation. So what we do is find the summary of each procedure. And a summary really is a collection of these incorrectness triples that you just saw, a collection of specs. So to do that, we have a summary table T, which we initially populate with those local axioms that you just saw. So you can think of those as the building blocks. Initially, you just have the specifications for heap operations. And as you iterate and analyze each procedure in isolation, you build summaries for procedures and add them to T. And the nice thing is here, and this goes back to what I was telling Zach, here, because we are in the under-approximate world, for instance, when we have recursion, we can unroll it a bounded number of times. It doesn't really matter if we capture all behaviors. We're interested in some of the potential behaviors. And like I said, the bioabduction mechanism is nothing new. It's exactly the bioabduction mechanism of infer, except that we can do two things that infer couldn't do. Because we are in the under-approximate world, we can easily drop execution paths or branches. Like you have an if-then-else, you can focus on one branch only. In fact, this is one of the things that you can tune in Pulse X and say, okay, the maximum number of paths that you should consider at any one time, set it to 20 or set it to 50. And we did some analysis on what's the optimal number of branches that you should consider at any one time. Same for loop unrolling. You could just consider unroll it in a banded fashion. Okay, so enough business talk, sales pitch. Let me actually show you an example. So I should start with a disclaimer saying that the examples that I show you are really stylized and simplified. In reality, these are many, many lines of code, and I'm only showing you bits that are interesting in terms of what led to the error. So, we don't only have 2-3-line procedures. It's much bigger than that. So this is a procedure in OpenSSL for some weird reason called xset prepend. All it does, or at least the bits that we're interested in, is that it allocates some memory, calling this procedure appmalloc, and then zero it out. Just use memset to write 0 to that bit of memory. But the problem is, so the appmalloc itself calls something called cryptomalloc, which is a malloc wrapper, and it turns out that cryptomalloc can return null. So if cryptomalloc returns null, which means appmalloc returns null, then here, when you try to set it to 0, you can get a null pointer dereference. Simple as that. So obviously, we came up with a specification for appmalloc saying that you don't need any resources to begin with, and afterwards it's possible to get null, because remember, this is about reachability rather than every execution path. So it's possible for appmalloc to return something that is null. And so as a result, memset, if you give it something null, it will get a null pointer dereference afterwards. If you try to set something to 0 that is null, surprise, surprise, it's a null pointer dereference. So combining these two end-to-end, we can get this spec for xset prepend that says, okay, you can start from empty and get a null pointer dereference at this line here. We also actually record the line numbers usually. Hello?
So I'm guessing that when you analyze appmalloc, there was a disjunction about that. How did you decide what
So we don't model disjunctions in the post state itself. We just generate multiple summaries. So we had multiple summaries. One of them said you have null. One of them said you return an arbitrary value. And, there is a search algorithm. That's what I meant by proof search, that considers different things, different combinations. And that's also what I meant by, a bounded number of paths, potentially. Okay, so now with this specification, we were convinced that this is a true positive. You can definitely have a null pointer dereference. So we went to the OpenSSL developers and said, hey, we found a bug. But you're bound to do this when you're doing static analysis, right? And the developer, this is my co-author, Locke, the developer came back quite infuriated and said, nah, this is a false positive. This doesn't happen because this appmalloc doesn't return if the allocation fails. So it will never expose this null. And we were really puzzled by this because we actually had a trace showing that this is happening. And it turns out that there are 2 appmallocs in 2 separate files, in these 2 different files, and 2 appmallocs. And the program was calling the wrong appmalloc, and the developer thought it was calling the right one. So eventually he had to concede and say that, yes, we need to make sure it is calling the right one, it is calling the wrong one, and we need to fix the one that is being called here. So he submitted the fix himself, and of course, we're very happy with that. Again, this is a very simple bug. Of course, there were multiple lines of code that I'm not showing you. There were loops and recursion and whatnot, but that was the gist of it. And you can see it's a very, very simple example. So I've been going on about no false positives, and this is the main criterion, main selling point of incorrectness separation logic, right, that we have no false positives. So at the beginning, we were convinced, okay, anything that ISO finds is by definition true positive, so we should be reporting it, right? But it turns out that's not exactly the case. So whether or not it is a false positive, but should you report it? Not always. And let me tell you why. So here's a very simple example, this foo procedure that takes an argument and then just dereferences it and writes 42 to it. Very, very simple. So using this axiom that you saw from before, it's possible to get a null pointer dereference when x is null. This is the right axiom. So I can obtain a spec for foo that says if the argument that you passed is null, then you'll get a null pointer dereference. Unsurprising, right? So now we put this question to 2 separate entities. Should we be reporting this null pointer dereference or not? Well, the developer could come back to you and say, no, you shouldn't, because I never call foo with a null argument. Even though this error can happen if you pass it null, I'm careful in my programs. I never call foo with a null argument, so don't spam me with this. I know what I'm doing. But then this really makes things hard for us, because when do we report? It is a true positive if you give it a null, but how do we know if it's being called correctly at all times? So the problem is that in order to be able to confidently report it to the programmer, you want to kind of make sure that the error happens for all possible input values, or at all calls, that there is at least the call side that is calling it in the wrong way. So you kind of need to analyze the whole program and see there's an instance like that or not. And this is exactly what we wanted to avoid. So instead what we did, we changed our reporting criteria. And we came up with this notion of manifest errors, intuitively meaning exactly what I just said. That something is a manifest error if it occurs for any input state rather than for a particular input state. Because if, regardless of the input, that error crops up, then you can confidently go back to the developer and say, hey, this is an error. And he can't then come back to you and say, no, because I don't call it with this particular value, because you're not limiting the input. So formally, this means that if I have an error triple, it is manifest if for any initial state S, I can find some post-state S prime that leads to an erroneous execution. So regardless of the beginning state, regardless of the input, you will get into an error. And that final state is included in Q. So in the case of the example that you saw, I'll come back to that, the SSL, XZ, prepend, what a name. In that case, you saw it had no dependency on the argument, and the error could always happen, and I'll show you that in just a second. But you can see that, okay, on paper, this is very easy to specify, but it's not exactly the easiest thing to check, because it says for every beginning state, something, something. And this is not practical. You can't enumerate the entire state space and say this happens all the time. So instead, we came for an algorithmic way of checking this, as in, that is to say, we check a bunch of conditions that, if satisfied, guarantee that your error is manifest. Specifically, following in the footsteps of infer, our post states are typically of this form. You have a bunch of existential quantifications in pre-next normal form, typically, and 2 bits of assertions. One spatial bit that talks about the heap, your points 2 bits, and one pure part that talks about your Boolean assertions like x is greater than 42, etc. So if your post state is of that shape, then provided that some conditions are satisfied, that's going to be a manifest error. So the first condition is very simple. It says, well, the inputs or the initial state should not have any constraints. It shouldn't need any particular form of heap or any Boolean assertions. Because, for instance, remember that error that I just showed you with the foo says, if x is null, then I get an error. So you want, this part of the assertion won't be true. It has a particular constraint. And same for heap, because, for instance, you could say, oh, well, if this error can occur if x is already deallocated, and the developer could say, well, I never call it within the allocated x. I always pass the proper resource. So this might sound a bit too strong, and we have relaxations of this, but a very straightforward way of ensuring that what I said doesn't happen is by requiring no additional resources to begin with. The second condition says that, okay, your post condition needs to be satisfiable, otherwise you have a vacuously true post incorrectness triple that doesn't really says anything, and that the locations in your assertion, meaning the left-hand sides of the points to assertions, is existentially quantified. You don't reach the error under the particular assumption that only if location 42 was allocated, I get into that error. So you don't make any assumptions about the way that your allocation works, for instance. And finally, you can ignore the maths. This very straightforwardly says that basically I have no constraints in the Boolean part of the post condition. So I can replace these existentially quantified locations as well as the free logical values of Q with arbitrary values, and it would still be satisfiable. So this won't hold if, for instance, this is saying that x is null. Like x is 42, right? If x is a logical variable. Right, so this is the exact same thing that I just said. It's in the paper that says if these conditions hold, then what you have is a manifest error, and you can easily report it to the user. So if I go back to the example that I just showed you here, this is a manifest error because intuitively, like you saw, I'm not even looking at the arguments. The input. The error it's possible for the error to happen regardless of what you call the procedure width. And you can see, well, there's no locations here, there are no logical variables here, so the conditions that I just showed you trivially holds, and I am starting from emp and true anyway. Right, so the dual side of manifest errors, what we call latent errors. So if something's not manifest, it's latent, meaning that it can occur only for certain inputs. And you saw that, for instance, in the case of the foo example, that only happens if you pass it null. Another example is something we found again in OpenSSL, which is this chop-up args. It takes this argument args, and which has two components, the count bit and the data bit. If the count is 0, it sets it to 20 and allocates some stuff using that procedure that you saw. And then afterwards iterates over that data bits and sets them to null. Now, if you remember, because this can return null here, the SSL except, you could potentially get a null pointer dereference here when you try to access it. Right. But, so is this manifest or latent? Does anyone want to brave an answer? Manifest. Why? I see. Ah. Bad luck. It is. It is indeed a latent error because it only happens in this if branch. So it only happens if the count components of arg is 0. And the developer could argue that, well, I always call it with the right arg. It's never 0. So because it only occurs if this branch of execution is taken, this is latent. So it depends on the value of this count, i.e. the value of the argument that you pass it. So we wouldn't be reporting this. But if later on, if you step out and look at the, like one layer up, and you see an instance of chop-up arg, and you can prove that, you can show that arg is indeed, the count is 0, then we will report it as a manifest error. Okay, so I also said that even though I didn't show you the formalism, we can use PulseX for detecting memory leaks, and I want to show you an example of that. Specifically, this is an example that Infer couldn't find, even when it tried very hard. Anton? Yeah. I see. So you're saying that essentially the users can help you with writing annotations that are specifications of the program saying that I never call this but yeah, I mean yes. The short answer is yes. We haven't done it, but it is like as part of the Infer infrastructure, which PulseX is built on top of, it is possible for you to like write your own summaries. So you can actually say, but these are the only summaries for this procedure. So only these conditions hold. So that would be, we can work on that if we want, on that extension. Right. So like I said, I want to show you also an example of a memory leak. This is in the the names are terrible. The WW body procedure of the S server application, which is, like a way of for implementing a generic SSL TLS server. So this is many lines of code. I'm only showing you the relevant bits. So in a nutshell, again, don't worry about the stupid names. We're creating a buffer, IL. We're creating a buffer entry, this BioFSSL. We're pushing it onto the buffer. We do a bunch of stuff, and at the end, we call free all, which says deallocate every entry in the buffer, so that we don't leak anything. Right. So what happens is that, again, this push silently does nothing if the I/O is null. So if you try and push SSL bio into I/O, and I/O is null, then it does nothing. So SSL bio ends up being dangling. It's not being pointed to by anything. So as a result, later on, when you call free I/O on a null thing, it's not going to deallocate SSL bio because it's not part of the buffer. So you end up potentially leaking SSL bio when I/O is null. And this was a nice example because it's more than 400 lines of code. Not that the number of lines is impressive, but there are multiple procedure calls that manipulate I/O, some of which are recursive, and we have multiple loops, nested loops. And PulseX could effortlessly find this bug because it did bounded unrolling of the loop, whereas Infer couldn't because it could not come up with a spec for that loop and notice that essentially SSL bio is being leaked. So again, simple examples, but because of the under approximate simple analysis, we could find it. Yes? Can you repeat the question?
I/O cannot be null according to the
Okay. So you're saying essentially if the developer could show that this new thing never developed and never returns null. Right. But we generate the spec for this ourselves. So we have looked at the code and we are convinced that you can come up with a spec where it can generate null, and that's a manifest error, essentially manifest specification. So you're saying what's the difference between this returning null versus... So there, the spec that we come up with, I think you're talking about the manifest errors, as in why do we distinguish there and not here. There is the behavior that we generate is contingent on a particular value. Whereas here, well, first of all, this doesn't even have any arguments. So that behavior that we came up with, the fact that this bionu can return null, is essentially something that we can guarantee. There is a path that could return null. I hope that was clear, unless I misunderstood your question. Okay, right. So I talked about pulse X and its no false positive guarantee, our reporting criteria for manifest errors. But remember the asterisk? I said there are some caveats, and now I want to talk about caveats because theory and practice don't always love each other. You can have the best intentions, and the practice could still fail. So the first reason for that is because occasionally we have code that is unknown. So we have this black box operations whose implementation, whose code we don't have access to. So we cannot go over it and generate its summary and know its behavior. So in such cases, we just treat them as skip, which could be a cause for false positive because we're not accurately capturing the possible behaviors of that program. The second source of false positives is a very practical one. It's because of the arithmetic solver that we're using. And this problem is kind of orthogonal to the under-approximate or over-approximate world. It's got nothing to do with that. Because as you know, when it comes to solvers in general, we have two conflicting desiderata, right? We want it to be speedy and fast, but we also want it to be accurate. And we can't have both of these at the same time. We can have fast but kind of simplistic solvers or slow but accurate ones. So we had to kind of decide which one of these we want. So we went with Tony Hoare's advice that should I read this out? Yes. Scientists seek perfection and are idealists. An engineer's task is not to be idealistic. You need to be realistic as you have to compromise between conflicting interests. And this is exactly what we were trying to do. So we chose speed because we wanted to have a practical tool, but it meant that our arithmetic solver, especially over inequalities, could have some potential false positives in it. But like I said, we see this as an orthogonal problem to under-approximate versus over-approximate reasoning. Okay, let me see. Yes, I'm right on time. So I've shown you ISL and pulse X, but I also wanted to give you like a 3-4 minute summary of the extensions of ISL that we've been working on. Specifically, Peter said that, I'm a concurrency expert. So obviously, as soon as I started working on ISL, I had this bug, I had this itch that I had to go and see how it looks like for concurrency. So I've worked on 2 extensions to ISL, and I want to just show you an overview of what those things are. So the first one is extension to concurrency for detecting things like,
Sorry, before I just got a quick question on
Sure.
Do you have an idea of the false negatives to this?
No. I mean, the point is we're doing under approximation. We cannot know what we're missing out on. I think it will be... Yes, I mean, there are cases like, remember that I said comparable, but it's not exactly like every bug that we found was, a subset of infer or vice versa. There are things that infer could find and we couldn't, and vice versa. That's what I said, comparable. So in that sense, we have some anecdotal evidence of, we couldn't find this. Like I said at the beginning, they are comparable and in some cases better. So it's either about as many, it's not exactly like we found 50 and infer found 50. It was like 52 versus 48, something like that. And sometimes in favor of infer, sometimes in favor of pulse X. But pulse X was often much faster because of under-approximation, and it had a higher fix rate. Because the number of bugs found is not the number of true bugs found in infer. You still have to analyze and ask the developer, is this a real bug? Whereas here we didn't have that problem. So the fix rate for pulse X that's, in my opinion, more important criteria because it shows that actually what we found was a real bug because it was fixed, rather than something that we just spammed the developer with. So since I'm running out of time, I'm just going to blitz through this bit. For those of you in the room who are familiar with concurrent separation logic, it essentially has this other principle that says if you can prove stuff about 2 different programs, C1 and C2, you can compositionally combine them together and prove something about the concurrent program by composing the pre and post states with the star separation. So we wanted to kind of have the same thing in for ISL, so we came up with concurrent incorrectness separation logic, or CISL for short. And here's the famous slide that Peter was talking about, Ilya's famous slide. So I was very happy that he mentioned it. And the question for us was, okay, there have been a million extensions of concurrent separation logic. Which one of these should we go for? You know, this is a very meticulous genealogy of concurrent separation logic. And this actually annoyed a lot of people. People like Matt Parkinson, who are experts in this area, wrote a paper saying, why are we doing this? What are the next 700 concurrent separation logics that we're going to work on? And we wanted to avoid this pitfall and not have 700 concurrent incorrectness separation logics. So what we did, we came up with this general framework that is parametric, and you can instantiate it for different use cases like data races and deadlocks. I won't be able to show you that, just to say that we have instantiated to find data races, to find deadlocks, to find memory safety bugs for concurrent programs. And retroactively, we have managed to show that actually static analysis tools such as RaceD, who Ilya has developed, as well as this other deadlock detection tool, under approximate tool at Facebook, they're all instances of CISL. They can be recast into this framework. So we have some evidence that this framework is useful and it really can underpin real analysis. There is a caveat. It couldn't capture a certain class of bugs where you have these control flow dependencies between different threads. That's one of the reasons you changed the conditionals to stars, Ilya. This was a private conversation. So what we did then, we generalized that yet again to concurrent adversarial separation logic, which subsumes CISL. It's even more general and can find all these other bugs as well. And what we did as a use case, we instantiated to detect exploits, which was really interesting. So we can use it to detect buffer overflow attacks, information disclosure attacks. And I'm currently doing some consultancy at Bloomberg, where we're trying to use these techniques to actually build exploit detection tools, as well as exploit generation tools. So how can we automatically generate future exploits that we're not even aware of yet? So with that, I'll finish up. You've seen ISL, I'm not going to parrot it. You've seen PulseX, and I also showed you a little bit of possible extensions. I'm happy to talk to you offline about any one of these extensions. Thank you for listening, and apparently I'm not allowed to go to my last slide, but thanks.
All right, thank you. Questions? Yeah, Chendong.
So, Azalea, thanks for the very interesting work. I just could you help draw a conceptual comparison of this from the things that people do in the testing field, right? From testing, fuzzing, symbolic execution, and so on, right? And that's at the conceptual level. And also in practice, how would this compare to things like fuzzing, right? Fuzzing is finding a lot of bugs.
That's a very good question. This is kind of actually one of the things that people at Facebook are looking at, fuzzing, because fuzzing by definition is an under-approximate reasoning technique. And, there it's a little, I don't want to say informal, but, it's based on heuristics. You kind of try to find things that would allow you, like, to trigger a bug, whereas here we kind of doing proof search, but incorrectness proof search. So they are using the same approach. They're both under-approximate. They're both using bug detection, but the the formal underpinnings are a little bit different. In terms of what's more performant or what's found more bugs, this is too early to say because, we have just one prototype academic tool. So hopefully people at Facebook will have a better answer to that.
Just a follow-up. This sounds like quite similar to a lot of tricks that people do in symbolic execution and concurrent testing, right? You can drop some predicate and so on. So it sounds quite similar.
Exactly, and that's another thing that I'm hoping to look at. If any of one of you are interested in doing a PhD with me to look at topics like that, I've actually put out an ad where, because Christian Kadar is at Imperial, and it feels like a missed opportunity. So we wanted to see how can we, use some of the principles and the lessons that we learned here, and with things like concurrent testing, and concurrent execution.
Also, thanks for the talk. I would like to ask something about manifest errors. So I find the definition a bit too strict, if I got it correctly, because it seems that, for example, by definition, you will only find the very most stupidest buffer overflows, right? And a buffer overflow is something I really want to find, and it will not be triggered on all inputs.
So by buffer overflow, so the buffer overflow stuff that I was talking about was the concurrency, like the adversarial stuff. There we were mostly looking at memory. This is kind of unrelated to your question, but there we were looking at memory safety errors and leaks and stuff. But you're right, it is draconian. It has a very strict condition that you require no resources. So in the paper, we actually come up with a more practical condition. We call it a relaxed manifest error. That the errors that will still are actually really errors, and you have to report them to the developer. For instance, I'll give an example in just a minute, but it doesn't have that strict condition. An example would be, if you have an argument, X, you try to read from X and then immediately deallocate it twice. So that's, if you free it twice, that's always going to be a bug, regardless of whether or not, X was initially to deallocated to begin with. But the summary for that would require X points doing the precondition, which kind of contradicts the assumptions that we had, because it says you have to first be able to read from X and then do double deallocation. So we have relaxed that condition to catch bugs like that as well, that are guaranteed to happen. But I didn't go through that in here.
And quickly, coming back to the question that was asked during the talk by the colleague on my left, I understood him differently than you, I think. So did you also consider in cases where you see, there's one input triggering this bug, we don't report it as bug, but we generate the annotation.
Yes.
That you consider too?
Yeah. We generate the annotation, we file it away in our procedure summary, so that later on, if we do find a call which calls it with that bad argument, we can say, here it is. You said you don't do it, but you do it.
Hey, so I have a question at the start when you're showing the issue with the free when you have. Mm-hmm. So why is it because incorrectness logic is kind of backwards to separation logic there. Why is that not an issue in separation logic when I'm allocating? Because I kind of get a points to, and then I could frame.
So in Hoare logic, in all these correctness logics, if you have a triple with false precondition, that's vacuously true, because it says every state in false, blah, 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 blah. That is immediately vacuously true. In correctness, because of the backwards interpretation, you have an existential over false. So it's a for all versus existential on the false. The for all is vacuously true, the existential fails because you can't witness it. That's a very technical reason, but that is because it's a backwards reachability versus forward execution.
Actually, I have a question about the same point. So you're phrasing the incorrectness separation logic as a classical separation logic, right? Which means that the free is exactly the point where you lose resources. Mm-hmm. How would you do that for an intuitionistic logic? Do you see a chance to also do, because that is not so easy to track which resources you lose, right? You might call a method and you just don't get them back. Do you see a chance to also apply it there?
That's a very good question. So basically, in an intuitionistic logic where you can forget resources and you can drop this deallocated resource, I haven't thought of that, but I think that's a very important question because of things like Iris, where you have this intuitionistic styles. I haven't given it much thought, to be honest. That's really intriguing. I would be interested to know what that looks like.
So one of the next 700 then might be intuitionistic. Yeah, Ilya. Yeah, for the recording.
All right, very quick question. Really cool stuff. So I think the adversarial separation logic, this is something that is coming at SAS later this year, right?
That is adversarial logic of Julian Bang. Right. No, it's not this. That one doesn't have separation logic. It's not compositional. It has some decisions that I disagree with, but Castle concurrent adversarial separation logic is something that, I pestered Julian saying, you should not be doing things like that. You should be doing it this way. So we have worked on that together as well.
Build the castle the right way. Anyway, so that was not the question. The question is coming from synthesis perspective. When you say that you're generating exploits, do you mean generating the inputs that trigger the bug or generating the actual code?
So we haven't done this work yet, but the plan is this AUG techniques, automatic exploit generations, is typically to come up with an adversarial program. So you have a piece of code and you want to see if it can be exploited or not. And the point is to come up with a potential adversary, a program that could attack your program. So you want to generate, it's kind of a synthesis problem. You want to generate a bad agent that would exploit some vulnerabilities in the code that you have.
All right, thanks.
Okay, so one last question. Two more questions.
Okay. I somehow don't understand when there is this under-approximation happen. How are we not losing, how is it sound, how are we not losing context sensitivity? If I have multiple methods calling each other, I'm losing the context from where I'm coming. Isn't this over-approximating?
No, so the way we do it when I said proof stage, remember parts and methods. So we generate the summaries for each method in isolation, and then we can look at the ways in which they can be glued together. Not necessarily all possible ways. That's the under-approximate approach. But we can see, okay, well, this procedure has this summary, and this one has this precondition. If the pre and posts match, you kind of glue them together using essentially the sequential composition rule of separation logic. So you don't generate every possible summary, but you don't lose any context information here, because that's essentially what by abduction does, right? You generate summaries and you combine them together by end-to-end gluing them with each other. I don't know if that answers your question, but we don't claim to find every possible summary, but the ones that we find are definitely reachable, are not over-approximate ones.
I have a question regarding the understandability of the error messages. So in verification, typically it says can't prove your property, and then you have to go off and map it back to concrete inputs. Mm-hmm. Do you get an advantage here, or is that basically the same step?
So we actually can give you a full trace saying, here's a trace that gave you the error. Because we essentially, because of the using symbolic execution, we have exactly the pre-state that leads to that condition. We can say, okay, if you call this procedure with this input, then it triggers this other bug in this other procedure, and we give a full stack trace of, here is how the bug can be found. I didn't show you that, but that's what we do. So in that sense, I think it's quite useful. And that's what convinced that OpenSSL developer. That, we're like, here's a trace. You can't dispute that.
Has that something to do with that you are mostly interested in these manifest errors that basically do not have any input dependencies?
So it's kind of orthogonal there, because we can still give a trace that is for that particular input. So you can have a trace even for a latent error that says, if you call this procedure with this argument, you'll get an error trace. And then they can say, well, you're only assuming that I'm calling it with that input, but I never call it with that input. So the trace business is a little bit orthogonal to whether or not it's manifest or latent. That's something we do when we try to report, as in we look at summaries, is this manifest, should we report it or not?
Thanks.
All right, good. So thanks again for the great talk.